Good evening, everyone. Welcome back to NPTEL live session. So this is week 3, and again we will be talking about the basic concepts that have been covered from lecture 11 to 15, and then after that we will be solving the problem. If there is any question or any doubts that you are having regarding the last two sessions, you are free to ask me or put your question in the chat box before starting the lecture. If not, then we can move ahead. And for others to join, I'll wait for 3, 4 more minutes. And thank you for joining. Okay, so let's get started. The topics that we are going to cover today, they would be mostly surrounding cyclopentadiene complexes. So we will be talking about the transition metal. We are writing a short form of TM, cyclopentadiene complexes in their preparation methods, meaning how they are prepared, their reactivity, how they react, their bonding properties, which molecular orbitals participate, and what kind of bonding they are having. And this is the whole essence of the lecture today. And at the end, we will be talking about the problems and how to solve those. What is the approach that we need to have? So, first thing that we can start with is your bonding properties. Firstly, we'll see the bonding properties in the metallocene itself. Sandwich complexes of cyclopentadiene, they are known as metallocenes. Say, for example, if we have iron Cp equal to, where Cp is your 5-membered ring. This is cyclopentadiene. This is Cp negative, right? This is your cyclopentadiene. And this name, since metal has come into picture, so this name is called as ferrocene. That's where we are talking about the bonding properties in metallocenes, meaning metal has been coordinated with your Cp group, which is your cyclopentadiene. So it has been said that we have mostly, besides the sigma bonding, Cp groups are known for the pi interaction. That means pi interaction is favored, meaning that is a dative bond. Dative bond is something from ligand lone pair, it is going to the metal empty bonding or empty orbitals. So we have Cp E1. E1 is a molecular orbital of the Cp, which is giving electrons. This is called a dative bond shown by arrow to iron, either in dyz or dxc. These are the two orbitals where Cp can provide its ligand. And this kind of interaction is very, very strong. There is a strong bonding. So there is a very strong bonding. Okay. So say for example, if we have a ligand, and ligand is having lone pair, that lone pair is going to the metal. That is a pi bond, dative bond, and it can be vice versa also. But in case of Cp, it is having additional electrons in E1 molecular orbital. These are ligand-based molecular orbitals, which have been generated from the symmetry-assisted linear combination that you might be knowing from the group theory. And whatever the pi orbitals are there, which can make the pi bond, in that orbitals we'll be getting the electron density. So let's look at the orbital picture, how it looks like. So firstly, since we are talking about the exclusively pi molecular orbitals, both of ligand as well as metal. So let's first see how ligand molecular orbitals look like. So each carbon center having p, that is the low, because p orbitals are involved. And firstly, if you are making one pi orbital, so this would be first condition. And the other condition would be or where 4 orbitals participate, not the 5th carbon. Shaded half, and this is shaded, or it can be other way around also. So this is your category of E1G, and they bind. So d orbitals, it is in between the axis. So if I'm saying this is my z-axis, this is my y-axis, so this becomes your dyz. Similarly, if you have something like, so this is showing you that it is coming out of plane. So this is your DXC. Like if Y is in this direction, according to your board, Y is in this direction, Z is in X direction, like right direction. So the X is going to come out of your board or out of the plane. Therefore, we are making it little above onto it so that it is more clear. So these are the orbitals which are going to, and these are the metal orbitals. The yellow ones are metal orbitals, and the white ones are the ligand pi orbitals, that too in the category of E1G. Now we have another G, meaning that it is having a center of symmetry. And if you will see, if I go from the center and it is going to this direction and this direction, the lobes are same. Like it can create the same lobe if it passing through the center of symmetry. That's where G has been used. And if it is used, that means there is no inversion center existing. That is too much of the group theory, which we are not going to talk about right now. That's another course. So that was a one molecular vital that can bind with your DYZ and DXZ, which we earlier mentioned that E1 groups, they bind, they give the electrons, they make a dative bond, which is a very, very strong bond to DYZ or DXZ of the iron. Now moving to a next type of pi bonding, which it makes with the, because metal is not just having a d orbitals, it is also having a p orbitals, which can also make a pi bond. So if we have a ligand and now we have to bind it with metals p orbitals. So metals p orbitals PZ, we know that it makes a sigma bond. So leaving that out, we have p pi, py, it is in y direction. And if we are taking, this is your x, so this is your px. So these both can make pi bond. In ligand category, we have if they are making bond, the similar orbitals that we saw earlier, two of them are shaded, three of them are down shaded. It's a type of orbital. And the other category that you have already seen, right? Or we have where only 4 carbons are participating. Or right. So these are the metal systems, these are the ligand molecular vitals which are going to make the pi bond with py and px, and these are called as EU. Once they make it, there is no inversion center. That's why the notation is EU, whereas the other one was having E1G. So that is it. Now, if we, after the pi bond, we have another thing which is called the sigma bonding. And here, if we have a ligand, and another side, we have a metal. First, try the ligand sigma bonding. In sigma, that would be a head-on overlapping. So all the lobes would be facing towards one direction. or it can be other way around. All upper parts were shaded. So this is called as A1G, and A1G makes bond with PYX. This is your S orbital, or it would make with TZ square. Also, it can also make with your TZ direction. So in crux, what we have in hand is regarding the bonding in metallocenes. Sigma bond is formed between L stands for ligand and its A1G will bond with metal ka S orbital, PZ orbital and DZ square orbital, and the pi bond, which is ligand E1G and EU with metal DXC DYZ for E1G, and for EU it is with PX and PY. I hope this is clear. If there is any doubt, please let me know. That's an important part. And one note over here, that sigma interaction in this particular case is almost zero, because Cp from A1G, that means your ligand, it goes to iron DZ square, and this is non-bonding. Does not participate in bonding, remains as it is. So these are important points that we need to keep in mind. Now we can take up some interesting properties of metallocene, bonding properties in metallocene. First point. So if we talk about the bond energy, if we are rotating a metallocene, the bond energy of metallocenes does not change, does not vary with the ligand rotation. If we are rotating the ligand, so its bond energy is not going to change. That is an important point. And the another important point is that from theoretical calculations, where we have calculated the bond energy in both the forms. So generally we have two forms of metallocenes. If it is in same direction and the theta angle is 0 degree, that means the phase between two systems, they are in same phase, that is eclipse. And or if we have one ring like this way and other is this to this, the angle is theta equals to 180 degrees, which is opposite. So that is called staggered. And it has been found that from theoretical calculations, it is more stable over the staggered one, right? Now we have something. So far we have seen the bonding properties of metallocene, and we also saw which bond is more stable, which conformation is more stable, which types of bonding it does. So that we have seen so far. So this is one. I'll show you in a slideshow mode. Okay, so this is the kind of MO diagram that we see, where you can see we have already talked about that ligand is having A1G, A2U we didn't talk about because it remains like not participating in that one. Then E1G we saw and E2U we saw. E1U we saw, and here A2U also. If you see that here A2U of ligand that makes a bond with PZ. So A2U of the ligand with the PZ of the metal. This one. I didn't draw here. This type, and another is this type. The same lobes when they interact with the PZ. This is your A2U, or if it is flipped. So these both are your A2U which bonds with PZ. So that's where we have A1G which makes sigma bond, A2U also, but with the P, these two make pi bond. So this side where you can see we have a CP group. These are the ligand orbitals. Since we have two CPs, we are taking two in picture. Here it is metal, iron, and this is where the lowest bonding orbital, which is sigma, A1G, then A2U, then E1G, E1U, and we have then we have E2G also, which is a dative bond. Then all the antibonding starts over here. And this is a staggered conformation d phi t, meaning that the angle is 180 degree. So now another thing that needs to be noted down. Generally, metallocene we will see with 18 valence electrons. Say, for example, if we have ferrocene, and if you see the structure of FeCp2, Fe will give you 8 electrons, and each Cp has 5 electrons introduced, meaning 18 valence electrons. But the weakly bonding or non-bonding nature of the mentioned E2 and E1 molecular orbitals that actually make the existence of metallocenes with less than 18 valence electron. That means metallocenes with less than 18 valence electron exist because of the non-bonding or less bonding nature of your E2 and E1. For example, we can show the chart here where we know how the bonding takes place. So here, if you'll see carefully, we are starting, this is the general configuration, which is, it is having A1G2, A22U, which we all just saw, and E1G4 and E2U4. That means 4 plus 4 plus 4. 12 electrons are already coming, and now we have to fill from the whatever it is left out. Say, for example, we have Cp2, titanium plus 1. Titanium plus 1 will give you 3 electrons. Right? So it is already, and there's a plus 1. So here 10 coming from this one and 3 coming from your titanium, that is 13. Already 12, this is 12 electrons already been filled. So what is left is E2G1. Similarly for the vanadium plus 2, vanadium plus 2 also will give you 10 plus 3, E2G1 would be the valence electron, valence orbital. Then we have Cp2V, where there is no charge. That means vanadium, all 5 electrons are going to, there it is vanadium plus, meaning 1 electron would be gone out. So 4 electrons participation is there. That's where E2G2 and vanadium with 0, meaning E2G2 and A1G star 1 would start happening. So this is a sequence, and there is 1 unpaired electron present. How many unpaired electrons are present? And based on that, we will be having what is the spin value and what is expected and found magnetic moment that you can go back and calculate. This would help you in understanding more about the magnetism. Moving ahead, now we'll see to the next topic, which is our reactivity of the metallocene. In the reactivity, uh, ferrocene, they have a high redox stability. So it behaves like an organic moiety. So it mimics the reactivity like an organic molecule. Say, for example, ferrocene, rudinosine, and osmosine. These are all one group elements. They will give you electrophilic substitution reactions, which means if you have we are starting with the more stable isomer, which is the eclipse form. Now we have this is an electrophile, and in CP the electrophile is H, so it is going to replace that. Firstly, it would undergo a transition state of where electrophile is being attacked by the electrons of CP, and it would work like H here, and E will be here and coordinated with 2 bonds, and the other side remains like this. This is a general mechanism. Since it has lost 1 electron, it gains positive charge. Now the H positive will be lost, and it regains, meaning it would create a minus charge again, and therefore it retains its CP nature. And here there would be a substitution of E. Right? So the point is, ferrocene actually undergoes this reaction 3 times faster than benzene because of the high electron density present on the CP ring. Okay. So there is another features also. I'm writing Fe ferrocenyl amine is more strongly basic than aniline, and ferrocenyl formic acid is weaker acid than benzoic acid. Okay. Now let's see the Friedel-Crafts acylation. As we said that it undergoes electrophilic substitution. So we have acyl chloride in presence of US acid AlCl3. We know that H positive is going to be replaced by CH3CO. So we will get either mono substitution. It's the same process that we have shown earlier, or we can get dye substitution in both the rings. Right? So this you have to be careful that there could be possibility of both the products. Also, it has been seen that if the electrophile used as an oxidizing agent, then the substitution reaction can be suppressed by the formed ferrocenium ion, meaning it can help in oxidizing the ferrocene and it would no longer be a substitution reaction. So the electrophilic substitution reaction will be suppressed by the oxidized product, which is ferrocenium ion, written as FeCp2 whole charge positive. So this is very important. If electrophile works as an oxidizing agent, so it can suppress the formation of your electrophilic substitution reaction product, and that would be suppressed by the formation of an oxidized product, which is ferrocenium ion. This is the oxidized product. Another point that we have is the electrophile always attacks from exo direction to avoid the steric hindrance. We'll show it here. For example, we have iron, Cp group, and this here. And now we have H, we have CH2, CH2, COOH. So this is one possibility. I'm making the bond like if it is at the back side. And this is your exo position. Right? This one is your exo position. So, and the other one that we have is if your H is above and the CH2COH is down,